So when we look at this protostome and deuterostome development, we can see that the mouth comes first in the protostomes with that spiral cleavage. And we can see these protostomes have two major clades. They become the ecdysozoa and Lophotrochozoa. And so you can see that some of these things have an ectoskeleton or an exoskeleton, like nematodes and arthropods, and they molt their skeleton. But then there's other things, these Lophotrochozoa, and they have little tentacles on their head end, and they're like a little crown of fingers, if you will, or projections that sweep water around, right? So they can try and get food and things. There is a branch of these Lophotrochozoa that are called trochophores, and they actually don't have the crown. They have, at their larval stage, almost like a belt that it's around their middle, and it has the cilia around it. Platyhelminthes are also included in this, and it is not because they have the cilia crown or even the cilia belt. It is because molecular data has shown that they lack other features, features, but have other features that all Lophotrochozoa have that ecdysozoa do not have. So our Lophotrochozoa are going to be annelids, Bryozoa, Brachiopods, and Platyhelminthes. And then our ecdysozoa are going to be nematodes and arthropods. They're the things that have these like exoskeleton and they molt. So in our depiction, you can see that the Platyhelminthes, the nematodes, the rotifers, mollusks, annelids, and arthropods are all in that protostome category, right? And they make up the ecdysozoa. Then the other end has the Lophotrochozoa. My goodness, am I having trouble with these today. Then our last two branches in our tree include the Echinodermata and Chordata, and they are the deuterostomes. So the anal end forms first. So Lophotrochozoa have, like I was saying, that crown of cilia, if you will, on the top where they're taking food or different things in. This would be like the hydra. Those are Bryozoans, Brachiopods, and Rotifers, and they use it for feeding, right? This like cilia waves around and tries to bring the microscopic organisms and dinoflagellates and things into where they are able to get them and eat them or ingest them. There are mollusks and annelids that have the trochophore larval stage, so they have that belt like of cilia around the middle, and then it's more used for locomotion. And then Platyhelminthes has neither, but they are also Lophotrochozoa. So the ecdysozoa are the ones that are going to be like insects, things that have a cuticle, which is like their exoskeleton, and they molt it or they shed their skeleton as they grow. Things like insects, spiders, crustaceans, and nematodes are all things that have this cuticle and they molt off. So Platyhelminthes are the flatworms, and the flatworms were really the first animals we see with this mobile, active predatory lifestyle. They didn't just stand around with little cilia trying to suck some food their way or sway it around in the water, right? They are bilaterally symmetrical, but they have a head. They have that cephalization. They have eye spots and ear spots, which are auricles. The eye spots are the ocelli. They have a cerebral ganglia, so like the early formations of that nervous system, and they have a lateral nerve cord. They have a gastric cavity and a transverse nerve. They have a mouth and a pharynx. This is incredible, this differentiation of systems that we see in animals starting now. These flatworms are triploblastic, so they do have a mesoderm. They don't have that mesoglia like gluey gel. They actually have that third germ layer. But they are acolumate, so they have no true body cavity inside. Their mouth and their anus and their digestive system are just one cavity. So the muscular pharynx opens to the gastrovascular cavity and distributes nutrients to all the parts of the body. It lacks respiratory and circulatory cells or systems, and it respires by diffusion. So you can see this is a much earlier depiction of animals than as we progress forward and start to see that specialization of different cell types and organ systems. They do have light sensitive eye spots. They don't actually see. They just sense light and know that, oh, food tends to gravitate toward the light. I'm going to go that way. They have chemoreceptors that can sense things coming nearby or sound waves coming by. And their cerebral ganglia are the preliminary nervous system starting to form and communicate between the cells in the flatworm or Platyhelminthes. So we can see there are multiple types of Platyhelminthes. The first type are those planaria, which are the flatworms that we think about. They also include flukes, two different kinds, an intestinal parasite version and a marine and freshwater version that are typically parasitic to fish. And then they have tapeworms, which are also parasitic to vertebrates. So any parasite is going to leech off another organism because it has no digestive system. It needs to absorb its nutrients, and a tapeworm just sucks them right across their epidermis or their skin. The next Lophotrochozoa that we see are the Rotifers, and the Rotifers give that ciliated crown look that is so typical in these Lophotrochozoa. So it looks like they have, as their cilia beat in their little crown, it looks like it's spinning around in circles. And what happens is it creates a current of water that makes the animal move back and forth, but also sucks water toward it, and it allows it to drag food toward its mouth, right? So these Lophotrochozoa rotifers do have a digestive tract. It's called an alimentary canal. It has a mouth and an anus, and it's all connected through their digestive system, and they just feed straight through. Boop, 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 just comes in and out, in and out. And they typically live in fresh water, and as they take the food into their mouth, it's absorbed through their digestive cavity, through the epithelial lining, and then just comes right out the waste, out the anus. Our next Lophotrochozoa are the Bryozoa. And they have a retractable lophophore. And they do have a column, which is a body cavity. And it's weird, but they are colonial animals that reside inside of a non-living case. So they are on the inside of a shell. They are microscopic, and they're filter feeders. Typically, you can see them encrusted on rocks in aquatic environments, and they are important to building the coral reef. They move the organisms around and filter feed through their lophophore. The next Lophotrochozoa are Brachiopods, and they also have the true column. They are small, and they live at the bottom of the oceans, right? In the sea. They have two shells, and it's like a valve. They have a dorsal and a ventral shell. And you can see the line of symmetry in a brachiopod is different from the line of symmetry in a bivalve. So these brachiopods actually do not open and have symmetrical sides. The bottom is a different size than the top. And so the dorsal and ventral unequal size means that their plane of symmetry cuts through the middle of them. It's a vertical plane of symmetry. They lack the ligament to close that those bivalves have. So they cannot open and close this way with that symmetry. Instead, they have an opening, and it's almost like one shell fits inside of the other. Our last two groups of Lophotrochozoa are the mollusks and the annelids. So mollusks are things like snails, clams, octopi, chitons. They have this soft body wall, and often their soft body is within a shell. They have this amazing foot that comes out, and it is how they move. It pushes it along and kind of almost like push and hop, push and hop. And it has a visceral mass, which holds all of its organs, and then a mantle, which is the dorsal side of the shell. So it's underneath and it protects that visceral mass. You can see there's bivalves, cephalopods, gastropods, and those are the things we typically see as mollusks today. But there are other things as well: tusk shells, monoplacophores, aplacophores, and polyplacophores, which are the chitons. And a lot of these things, some of them have gone extinct already, and some of them still exist as well. They are true coelomates, and they have a very small coelom that surrounds their heart. It's that special cavity that surrounds their heart, protecting it. They have an open circulatory system and a special excretory organ, the metatanaphoridia. Now think about nephridia. That is the kidneys, right? So they have this like excretory organ that's similar to our kidney or our excretory system. Okay. And then they have this radula, and that is like a special tongue that has teeth in it, like a tooth tongue that will kind of like sprockets come together in a gear, and that's how they digest preliminarily their food. So you can see that the heart is surrounded by the coelom, and the mantle just protects that cavity. You can see that they have a digestive gland and an outer protective shell. They have in their digestive tract a stomach and intestines. They have gonads that are for reproduction. They have a nervous system with nerve cords, and all of these things are helping specialize the different parts or systems of this mollusk. You can see in their mouth they have those teeth things on the radula or their tongue as well. You can see at the bottom how the bivalves and the cephalopods differ, how they have very similar shells and stomach and mantle and heart and coelom, but they do have some differences, right? The cephalopods have tentacles and they have a beak at the point at which they're eating. And then the bivalves instead have gills, which the cephalopods do as well, but they don't have the siphon in the same area that the cephalopod does. It's by their anus, right? And so they're just a little bit different body plan when you look at all of the different organisms. The picture on the middle at the bottom is a chiton, which was a special class of the Polyplacophora, and they're pretty much extinct for the most part. But we do see snails and clams and mussels and octopi and squids and things like that. Most mollusks have more than one gender. They can be hermaphroditic and self-reproduce, but most are different sexes, and they typically fertilize externally. They release into the water and fertilize that way. But some do, like certain snails, do have an internal hermaphroditic system, and some have still separate sexes and an internal system. So the trochophore larva can develop with a foot and a shell and a mantle and start to move kind of like that sea slug around, right? And then as they get older, they can become stationary. Although with mollusks, we see more of that multiple body plan styles.